Welcome to S1 Lesson 10. This is the binomial and Poisson distribution, and today we're going to be focusing on the Poisson approximation of the binomial distribution. Before we start, if you have access to the slides, it's a good idea to print them out. That way you can make notes for yourself of things that you need to remember, thoughts and feelings at the time, your own understanding of the video. But whatever happens, make sure you have got a pen, paper and calculator, because there is opportunities for you to try out examples and then mark your work from my solutions. So where are we in the syllabus? Well, we've now covered probability and discrete random variables, and we're looking specifically at the binomial and Poisson distributions, which of course are discrete random variables. Today we're going to be focusing on that Poisson approximation of the binomial. So, if a random variable x is distributed binomially, such that x is distributed binomially with n trials and probability of p, then if f is large and p is sufficiently small, the binomial distribution can be approximated by the Poisson distribution. Now, since we know the mean, so this is our mean here, of a binomial distribution is np, then the approximation would be x approximate distributed Poisson with mean np. Now, if we have these conditions, it's important to note that since the Poisson is an infinite distribution, so that means that it can go on forever, there's no limits on how many occurrences can occur, then the larger the number of trials, then the better the approximation. And so this just leads to some approximation conditions. It's generally accepted that the approximation is considered to be a good approximation when n is greater than 50, which is convenient because that's what the binomial tables tend to go up to, and the probability is less than 0.1. So let's look at a first example. The discrete random variable x has a binomial distribution with n equals 100 and p equals 0.05. Find the probabilities x equals 0, 1, 2, 3 and 4 using both the binomial and the Poisson distribution. Okay, so we should really start off, if we're working with a binomial distribution, we should state the distribution using this notation. First mark in any exam question is given for that statement. If we remember that the binomial formula is n choose r times the probability of success to the power of r times the probability of a failure, which is q, to the power of n minus r. So I'm not working through all of these, it's a lot of writing. We're just going to see the answers here, and so here are the probabilities when we do it with a binomial. Now, we can, as we said, approximate using the Poisson using the expectation of x. The expectation of x is 100 times 0.05, which gives us our mean that we're using for the Poisson. So the Poisson formula, if you remember, is calculated as e to the minus lambda, lambda is the mean, times by lambda to the power of r all over r factorial. Okay, so again, you can have a look here. Here's all the probabilities that have been calculated. Look how close the approximation is. We are 8 tens of thousandths out for this first probability here. 5 for the second. It increases a little bit here with 3 thousandths out for the third. We're 8 10,000ths out here, and we're 26 thousandths, or 26 10,000ths out on this one here. So you can see it's a fairly good approximation, certainly to 2 decimal places. This would be accurate enough for us, even 3 decimal places in most of these cases. Okay, so let's have a look at a different example. Find the probability that at least 5 double sixes are obtained when 2 dice are thrown 180 times. So, we need to start this question off. First of all, probability of 6 and a 6 when rolling a dice. These are independent events, so I can just work this out by multiplying probability of a 6 times the probability of 6, which is 1 over 36. Now, what we're saying, x is the number of sixes, then x is distributed binomially, The number of trials was 180, and the probability of a success is 1 over 36. Now the expectation of x here, and I don't usually always write out the expectation of x, but I'm going to just to emphasize things here, is 180, so n, times the probability of success, which is 36. And if you work through that, you get an expectation of 5. So what we can actually say is that x is approximately distributed with a Poisson mean of 5. Now, the question asks to find the probability that at least 5 double sixes were thrown. So I'm looking for the probability x is greater than or equal to 5. So I'm going to use the tables. To use the tables, I'd need to do 1 minus because it's greater than. So I'm going to get that upper tail by subtracting the lower tail from 1. I want to subtract all the probabilities up to and including 4. So that leaves 5 in the tail of probabilities summed up. So let's have a look at this in our table then. The column we want is the end column, so there's no need for me to use a highlighter to emphasize that. But let's just have a look, reading across less than or equal to 4. So just coming across, so you can see less than or equal to 4 is 0.4405. So 1 minus 0.4405 gives us a probability of 0.5595. And that's essentially it. That's all. All the work is in this step here. I'll highlight that in blue. So all the work is in that step there, actually just finding the expectation of x for the binomial so that we can use it for the Poisson approximation. Please remember you must state the original distribution. There will be a mark for that, and then you need to state the approximation. So there's 2 marks just for stating the distributions used in this question. Now you try one out. A factory packs nails in boxes of 300. The probability that a nail is defective is 0.02. Use a Poisson approximation to calculate the probability that box contains exactly 4 defective nails and fewer than 2 defective nails. So if you want to pause the video and have a go for yourself, and then resume it in a moment when I will go through the solution. Okay, so welcome back. We are looking at x being a number of defective nails. So if we just state x is the number of defective nails. Now we're told, in this situation, we know this is going to be binomial because they're going to be either defective or they're not going to be defective. So we need to state that it's distributed binomially. The number of nails that we're looking at is a box worth. So that's 300 nails in a box. And the probability that it's defective is 0.02. Now the expectation, or the average number of nails defective in each box, will be 300n times p, which is 0.02, and so we get an answer of 6. So we can say that x is distributed with a Poisson mean 6. First of all, we want to find a probability that x is equal to 4. As I've said previously, it's a good opportunity to practice using the formula at this stage rather than using the tables. So e to the power of minus 4, so e to the not power of minus 4, apologies, e to the power of lambda at this stage, which is 6. So e to the minus 6 times by the mean, which is 6, to the power of the value that we're referring to, so 4 all over 4 factorial. If you put this into your calculator carefully and work through, you get an answer of 0.1339 to 4 decimal places. Okay, part B said fewer than 2 defective nails, so we're saying probability x is less than 2. So really what we're looking at here is the probability that x is less than or equal to 1. So this is just a reading from our table, and let's have a look at how we do that. We've got a Poisson with a mean 6, so I'm just looking at this second column. Still put the green in just to highlight that, make it clear where we're reading from. I want to know probability x is less than or equal to 1, so I'm just reading across here, and I get an answer of 0.0174. So an answer to our question is 0.0174. Right, let's try out another question. An aircraft has 125 seats. The airline's records show that on average 2% of people booked on a flight do not turn up. If the airline sells 128 tickets for a particular flight, determine using a suitable approximation the probability that the flight is overbooked. Okay, so again, let's start off by stating the variable. So x is going to represent the number of people that don't show. So I'm just going to say x is no shows just for shorthand. People either turn up to the flight or don't turn up to the flight, so we know that this is x is distributed binomially. There is 128 tickets sold, so that represents n. It's not the number of seats on the flight, it's the number of tickets sold. And we know 2% of people aren't going to turn up, so that's 0.02. Apologies, should have 0.02 there. Okay, so at this point, we then want to calculate the expectation of x for our Poisson approximation. So the expectation of x, sorry, shouldn't put that there, get a little bit of a mix up. So the expectation of x is n, which is 128, times p, which is 0.02. So if we quickly do that on our calculator, we get an answer of 2.56. Okay, so this means that we can distribute this with a Poisson with a mean of 2.56, which unfortunately isn't in our table, so I'm going to have to do this using the formula. So let's just make a quick note of the formula. Probability x equals x, which is e to the minus lambda times lambda to the power of r, or x in this situation, over x factorial. Now, we're asked to find the probability that the flight is overbooked. So for the flight to be overbooked, we need 126 people or more. That means that there must be 2 or less no-shows. If we have 3 no-shows, then the flight's fine, but it needs to be 2 or less. So we're finding the probability x is less than or equal to 2. So this would be the probability x equals 0, plus the probability x equals 1, plus the probability x equals 2. Now previously I'd shown you how to do this by breaking down and just finding these probabilities separately, but actually if you find them in one line you can make life a little bit simpler for you. And the way we do this is, first of all, we write out e to the power of minus 2.56 times 2.56 to the power of 0 over 0 factorial, plus e to the minus 2.56 times 2.56 to the power of 1 over 1 factorial, times e to the minus 2.56 times 2.56 squared all over 2 factorial. And what you might notice at this part is that e to the minus 2.56 is a common factor, so I can take that outside of my bracket. Then if we work through each term, 2.56 to the power of 0 over 0 factorial is just 1. 2.56 to the power of 1 over 1 factorial is just 2.56. And then we get left with 2.56, not times, sorry, this should be a plus, 2.56 squared, and 2 factorial is over 2. And so this is far quicker and simpler to work out on your calculator. So now we can just type in this one expression, and rather than calculating all of the separate terms and then totaling them up, this you should hopefully find is a little bit quicker and simpler. So when you do that, you should get a probability of 0.5285. So the probability of the flight being overbooked is 52%, or 53% if you round it to nearest percentage. So 53% of the time overbooked. Which, if this was my flight provider, I wouldn't be too happy if half the time I turn up and the flight was overbooked and somebody was told that they couldn't get on the flight. Okay, well I hope that all made sense, because now there's one for you to try out for yourself. So, 95% of the population are right-handed. A random sample of 80 people were tested to see if they're right or left-handed. Use a suitable approximation to estimate that the probability of the number of right-handed people is I 79, or part 2, at least 78. Okay, so in this question, start off again by just stating, if you want to, just pause at this opportunity, because obviously you can attempt it yourself and then resume the video. Sorry. Okay, so 95% of the populous town are right-handed, so X is going to represent the number of people who are right-handed. And so this is distributed binomially. There are 80 people tested, so this is going to be X is distributed binomially. Number of trials is 80, and the number of people who are right-handed is 0.95. Now, this is all very, very well and good, but the requirements of the Poisson distribution is that P is sufficiently small. So actually, really what we need to do here is we need to think about Y and being left-handed. Okay, so just like previous binomial questions, we're just doing the reverse distribution. You can, if you want to, use Y complement instead. It makes no difference. Sorry, X complement instead. It makes no difference. But what we want to do is we want to define the reverse distribution. And it's simply because the probability has to be sufficiently small. At this stage, finding our expectation of X, number of trials, times the probability is 0.05. We should get that this is a mean of 4. So Y is distributed with a Poisson mean of 4. Okay. So in the question, we was asked to find the probability that there were 79 right-handed people. So probability X equals 79. Reversing that distribution would be probability Y equals 1. So this would be e to the power minus 4, because we're going to have to use the formula, as we'd say, and it's equal to it, times by 4 to the power of 1, all over 1 factorial. So nice and easy to type into your calculator. 4e to the minus 4 is all that's really required here, and you should get an answer of 0.07. Sorry, that should be a 733 to 4 decimal places. The second part wanted to find a probability that X was at least 78. So X is greater than or equal to 78. So just like before when we reversed the binomial distribution, what I want to do is I want to say, okay, well, Y is going to be, I'm going to reverse the inequality. It's going to be at most a value, and so the value that's going to be most is 2. So at this point, we can just take should be able to take a reading from the table. And so if we just bear with me 1 second. So here's our table. Let's just clear this off. So I want the column which is X less than or equal, mean of 4. And so I want the probability that X is less than or equal to 2. So reading across, we get 0.2381. So probability that X is greater than or equal to 78 is 0.23, I think we said 0.2381. Just double check, make sure I'm making no mistakes. Yeah, 2381. Okay, well I hope that made sense to you. Let's finish off by looking at an exam question. This is one for you to try. So let's have a look at it. It says it's estimated that 0.7% of the population of university students have a rare blood disease. In a faculty of 550 such students, use a Poisson approximation to find the number of students with the disease is exactly 4 or more than 2. So have a go at this for yourself and resume the video when you're ready to see how it's done. Okay, so let's have a look at the solution. We're going to say x is the number of students with the rare disease, so x equals rare disease. Now this is distributed binomially. The number of students is 550 and the probability is 0.007. The expectation of x is 550 times 0.007, so NP. Now when you work through this, we get a mean of 3.85. So we can say x is distributed with a Poisson, mean 3.85. Okay, so once you've done the first part, stating the distributions, got your first couple of marks, now we can actually answer the question. First of all, we want the probability that there are exactly 4 people with this disease. So we're going to use the formula. We're actually going to have to use the formula all the way through this question because 3.85 you're not going to find in the tables. So probability x is equal to 4 is equal to 3 to the minus 3.85, because that's our mean, times 3.85 to the power of 4, all over 4 factorial. If you type that into your calculator carefully, just work through it slowly, make sure you make no mistakes, you should get an answer of 0.1948 to 4 decimal places. Okay, next was probability that we had more than 2 people with the disease. So x greater than 2. Now, what we're going to do, again, this could go on infinitely. Really, can only go up to 550, but we're not going to work out these 550 or different probabilities. So what we're going to do is we're going to do 1 minus probability x is less than or equal to 2. So we're going to say 1 minus probability x equals 0 plus probability x equals 1 plus a probability x equals 2. And at this point we're going to use what I showed you in an example a moment ago. We are going to use that idea of factorising. So we're going to have probability x equals 0 is e to the minus 3.85. Now what you can actually do is you can actually speed this up a little bit. Because I know in each of these probabilities there's going to be the e to the minus 3.85, I'm just going to take that out. 3.85 as a common factor. And then inside the bracket what I'm going to leave is 3.85 to the power of 0 over 0 factorial plus 3.85 to the power of 1 over 1 factorial plus 3.85 squared over 2 factorial. So essentially we've shortened down now the writing of this formula because I've taken the e to the minus 3.85 out. I know that it's going to be in every one of those terms, and then I've just focused on the part which changes in for each probability. Now when we work through this, we get 1 minus 3e to the minus 3.85. We can just shorten this up a little bit before we put it in our calculator. So the first one is 1 over 1, which is 1. We then get 3.85 over 1, which is just 3.85. And I'd probably leave this, to be fair, as 3.85 squared, but just over 2. Now, when you work through this, you can type that all into your calculator in one go. Just take your time. If you really want to break it down and you want to calculate the second part here, first of all, please do. But this isn't a massive thing to put into your calculator and to be confident with getting an answer. When you work through that, you should find you get an answer of 0.7391, correct to 4 decimal places. Okay then, well let's have a look at the solution. So here you can see, first of all, and I'm going to go through and mark this, we're going to do this one by one. Two standalone marks, one for the binomial distribution, one for the Poisson distribution. So let's look at my solution here. That gets me one B1 mark, standalone. This gets me one standalone B1 mark. And on your mark scheme, when you're working through, you should tick them off so you know that you've covered those marks. Part 2, probability x is equal to 4, so we get a method mark for showing how we're going to use the Poisson formula. We then get an answer mark for getting an answer that's equivalent to 0.195 to 3 decimal places. So here's my method mark, and here, that's my answer mark, and I've got the 2 marks. Again, use your mark scheme, tick off the marks you're awarding so you can keep track of this like a checklist of evidence that you're trying to find in your working. So first of all, we have probability x is less than or equal to 2. So this is slightly embedded, this is embedded in my questions. So the method mark is given for that calculation and the answer is going to be 0.261. So we should get the method mark here. And finally, x less than x greater than 2 is given for the 1 minus probability of x less than or equal to 2. So there's our method mark here, and just at the end here, I get my answer marks for calculating that correctly. Okay, well I hope that all made sense. Remember, just go back to your mark scheme, check everything off and demonstrate, and just keep track. So at the end of here, we know that I've got 8 marks. And it's just a sort of easy way to use your mark scheme when you're marking your work. Okay, at this point, hopefully you're ready to do some independent study. So have a go at a Poisson approximation to binomial distribution exercise. And then if you attempt assessment 9, your Poisson approximation of the binomial distribution to check your understanding. Okay, well I hope that all made sense and that you enjoyed the video.